now formally introduce himself.
Thanks. So since this is a job talk, I thought I would spend a couple of minutes just introducing myself and giving you an overview of my career so that you can see where I'm coming from and what my accomplishments have been so far. And then the second sort of unconventional thing that I'm going to do in this talk is I'm going for breadth so that you can see the vision of my research, and that comes at the necessity of sacrificing a bit of depth. So I'm hoping that all of the slides will actually be understandable to everyone in the audience, even though I recognize that we've got a really diverse set of backgrounds. For those of you in NLP, I put pointers to my papers, so you can find all the details there. Okay, so I started my career in computational linguistics at Stanford University as an undergraduate. I enrolled in the Symbolic Systems program, which is an interdisciplinary major that combines computer science, linguistics, along with a smattering of psychology and philosophy. And this is a really great spread of disciplines in order to get into natural language processing. And while I was there, I took a class on statistical natural language processing. And in fact, it was the first time that it had been offered by Chris Manning, who's the author of the textbook on the topic. And so my interest really got sparked there, but was calcified when I moved to a small startup company during the dot-com boom. And we were aiming at building machine translation systems, or rather scaling machine translation systems to the web. And I really found that these data-driven statistical methods were the most effective way of rapidly prototyping things on a budget and with a small team. And in fact, when I was at this company, I first got introduced to the notion of statistical machine translation, and I tried to argue with my bosses that we shouldn't be licensing other people's technology. We should just build our own translation systems. They said no, so I quit and went to grad school. And actually, while I was there, I tried to start my own company to commercialize research in machine translation, which was ill-fated because Google, a couple years later, started giving it away for free. But it did put me in the enviable position of, as a PhD student, having 2 full-time software developers working for me. And to all the PhD students in the audience, I highly recommend this situation. And so actually, when I arrived at the University of Edinburgh, I was the only person working in the area of statistical machine translation. But by virtue of having this company and bringing my PhD supervisor around to its being an interesting topic, we started to build a critical mass. And in fact, midway through my PhD, I helped to recruit Phil Kuhn to come to the university. I tracked him down at a NIST machine translation evaluation, told him about the opening, and then did some smoky backroom deal to make sure there was student representation on the hiring committee so I could try to bias it so we'd hire him. I'm sure I'm the only reason he got hired. And then when I was there, I helped him write his first grant, and together we applied for a Johns Hopkins summer research workshop where we wrote this open source Moses decoder with a number of other researchers. And this has actually become a really standard piece of software that most of the people in the field now use. And in fact, the paper about it is now the 10th most cited computational linguistics paper. At the end of that summer workshop, David Urowski invited me to apply for a research faculty position at Hopkins, which I did and I got, and then went straight there after the PhD. So my first task was raise a bunch of money and start your own research group. So I raised a bunch of money and started to build my own research group. And at the moment, my research group has 8 PhD students, postdoc. My grants also support 1 other research faculty member. I have a full-time software developer and a kind of ever-changing cast of undergraduate RAs. And I've actually graduated a couple of PhD students who I inherited midway through their career and a number of master students. And together we've built the next generation decoder for statistical machine translation, which I'll turn to shortly. And while I've been a professor at Hopkins, I've been recruited to be on a number of boards. So I'm on the editorial board for our main journal. And I'm now the chair of the North American chapter of the Association for Computational Linguistics. And of course, all along the way, I've been writing a bunch of papers, and the productivity really increases when you have an army of graduate students working for you. So I also recommend that to all of the PhD students in the audience. And then one final slide. So in the ACL community, we have a curated citation graph, so a thing called the ACL Anthology Network. And I'm currently the 22nd highest of the several thousand authors in the network in terms of incoming citations. And I have the 19th highest H-index, which pairs me with a bunch of very, very distinguished people and puts me in very good company. Okay, so now on to the research part. So today I'm going to be talking about 4 separate topics that we're looking at in my lab. So first I'm going to be talking about building better models of statistical machine translation. And the mechanism here is we're going to be looking at different ways of achieving better translation quality, either with less data or pushing the learning curve up and achieving better quality with the same amount of data that's available to us. And then we're going to turn slightly and think about another logical way of improving translation performance, which is to increase the amount of available data available to us at low cost. And so I'm going to be talking about my mechanical Turk crowdsourcing experiments that Mitch mentioned. I'm going to then talk about 2 more speculative things. So one is trying to entirely eliminate the dependence on bilingual parallel corpora and instead estimate the parameters for our translation models from monolingual texts. And then to complete things, I'll cross out the other axis and talk about how we can use the data that we normally use to train machine translation systems to generate paraphrases which are useful for a variety of natural language understanding applications. Okay, so to start it off, I'm going to be talking about improving translation using syntax. And believe it or not, it's actually been a pretty contentious argument over the past few years about whether or not syntactic information has any hope of helping statistical machine translation. And there's roughly 2 camps, one represented by this crowd at the Information Sciences Institute at the University of Southern California, who sort of dogmatically believe that syntax must improve translation quality. It's just obvious, of course it must. So they've dedicated the past decade worth of research into building up machinery and a research platform that will allow them to actually demonstrate this. And then on the other side, you have people like Franz Ock at Google, who believe that our simpler data-driven models are always bound to win because we have more data from which we can estimate the parameters, and we don't require specialized annotation. And I think his position is just a friendlier way of saying what our dearly departed Fred Jelinek said, which was every time he fired a linguist, his performance went up. So the results that I'm going to be focusing on at the moment are Urdu to English machine translation. And so this is a result of a summer workshop that happened at Hopkins as part of the Human Language Technology Center of Excellence, where we got together 20 researchers from different universities and all tried to tackle the problem of how do we build the world's best Urdu to English machine translation system. And a lot of people tried various approaches, and I tried syntax. And in fact, this was my first foray into incorporating syntax into our statistical models. And it worked well enough that I'm going to show you the results first. So in statistical machine translation, we measure translation quality with an automatic metric called the BLUE score. And I'm not going to bother you with the minutia of how it's calculated, but higher scores are better. And just to calibrate your expectations, usually about a 1-point improvement is considered to be a publishable result. And over this 8-week summer workshop, we got a 6-point improvement, which was the biggest improvement that I had gotten in my career to that point. And in fact, it put us just a statistically insignificant 0.2 behind the world's best system for Urdu to English translation. And just to give a sense of the lay of the land, here are the results of a blind test administered by the National Institute for Standards and Technology. And there was a long kind of mid-ground, and then these 2 systems which had this dramatic jump. And those were our syntactic system and the syntactic system from the University of Southern California. And so for those of you who don't speak BLUE score, I've got some example translations here. And then you can even see from the headline of this article where we're getting first nuclear experiment in 1990 was, with the verb appearing at the end of the sentence. And then at the end of the summer, we have the first nuclear test was in 1990. So we're correctly reordering the Urdu word order, which is verb final, into the English word order. So the mechanism by which we experimented with incorporating syntax into our statistical models was using this Joshua decoder that's been developed in my lab over the past 4 years. So the Joshua decoder uses a particular representation, a particular formalism to do translation, and that's called synchronous context-free grammars. And these are a really convenient formalism for describing translation because they generate pairs of strings in correspondence, which allows us both to describe the word-for-word transformations that we have in translation, but also the reordering that occurs when you translate from one language with a different word order into English. Here's an example of a toy synchronous context-free grammar that I wrote by hand. So this illustrates some of the differences between Urdu and English. For example, Urdu is a subject-object-verb language as opposed to English, which is a subject-verb-object language. And you can capture that with things like this verb phrase rule, which on the Urdu side has the prepositional object phrase coming before the verb, and on the English side has the verb phrase with the object following it. Similarly, in Urdu, the PP rule is postpositional. So you have expressions like the store to, as opposed to English where you have to the store. So because we describe our translation process in terms of grammars, the action of translation is actually one of parsing. So for an input Urdu sentence like this, we analyze all the words by applying the non-terminal symbols which can dominate them in a bottom-up fashion. And if we simply stopped there, then we would have English output in Urdu word order. But by applying these rules like the PP rule, we transform the Urdu postposition into an English preposition. We get auxiliary main verb inversion. And then finally, we get the higher level sentence order of subject, verb, object in English from the subject, object, verb in Urdu. And then when we reach the S symbol, that's our goal state, and we have a complete translation. So in reality, in statistical machine translation, we're not handcrafting these grammars. We're not designing them with people in the loop. What we'd like to do is learn them automatically from training data. And the type of training data that we use in statistical machine translation is bilingual sentence-aligned parallel corpora. So we have 1 million sentences in Arabic paired with their translations into English. And from these, we're going to automatically learn a synchronous context-free grammar. So actually, the most popular type of synchronous context-free grammar is one that was created by David Chang, who's a graduate from the program here. He got his PhD in 2004. And his flavor of synchronous context-free grammar is called Hiero grammar. And it's really interesting in that instead of having a rich set of linguistic symbols, like non-terminals corresponding to noun phrases and verb phrases, he simply got a single non-terminal symbol X. But from that, he's able to extract, nevertheless, some interesting translation grammars. So the way that the Hiero system is applied to extract a synchronous context-free grammar is to take an automatically word-aligned sentence pair from our bilingual parallel corpus, to find a consistent phrase pair that bounds a box of these points, and then to assign a left-hand side non-terminal symbol to turn it into a grammar rule. And in this case, he's just assigning the symbol X. What then happens is you can pull out smaller subphrases within that, give them variables, and then come up with a hierarchical grammar rule that's more general than what you just observed there. And you can see here we're getting some reordering for Chinese, even if we're not using the linguistic formalisms that I described earlier. So what we'd like to do is transform this into something that actually has linguistic information incorporated. So we also can enumerate all of these consistent phrase pairs. And if we do so over all million sentences in our bilingual parallel corpus, then we can use relative frequency to estimate the probabilities of any given translation rule. So what we're doing instead is to actually generate a linguistically motivated syntactic synchronous context-free grammar. So what we do is we automatically parse the English side, and then when we pull out phrases like have diplomatic relations with North Korea, we can look up in the parse tree and see what node of the parse tree dominates that phrase. And then we can say that that phrase, that pair of phrases is going to be treated as a verb phrase. So even though we don't have a parser for the Chinese, we project via these automatic word alignments and ascribe it the English category verb phrase. And we can do similarly for larger phrases. We do run into one interesting confounding factor, which is for phrases like the few countries that or Australia is, we're unable to analyze that where it would be a perfectly valid translation unit under the HIRO model because we have no dominating non-terminal in the parse tree. So instead what we're going to do is borrow and abuse notation from a grammar formalism called CCG. So we're going to say that we're going to say the few countries that is a noun phrase simply missing a verb phrase to its right. So we're coming up with composite categories that will allow us to describe these things. So we can assign the category sentence missing a noun phrase to its right for Australia is. And then the great thing about this is we can then have exactly the same coverage as we had under the HIRO model. And I think this is an important factor to consider, especially when we think of all the years that people attempted to do syntactically informed machine translation, and we're finding that it didn't perform as well as the linguistically naive one. And there was a huge confound in the set of units that they had to construct translations was radically reduced by limiting themselves to nodes in the parse tree. So the really nice thing about this new training paradigm is that it's an incremental step beyond what we had before. So we are still using our automatically word-aligned bilingual parallel corpus, and now we're just simply adding automatic parse trees. And the great thing about it is we only have to rely on parse trees on one side. So when we're translating between English and a low resource language like Urdu, which doesn't have a parser, we're still able to apply this methodology. And here's a slide that illustrates some of the actual output from our system. So the red tree represents our syntactically informed translation, and the yellow tree represents the HIRO translation produced by David Chang's model. And you can see that we're getting a much better translation, and we're actually learning quite sensible things automatically, like that the verb phrase in English goes to the verb nominated, followed by the prepositional object, whereas in Urdu, it goes to the corresponding verb at the end of the sentence, which is preceded by the prepositional phrase object. So without ever explicitly telling it what the Urdu word order is, we're actually able to infer that and come up with a sensible set of transformations. So we introduced a number of further refinements to this by introducing semantic entities on top of these categories. And currently we're working on a more properly formal version of synchronous categorial and combinatorial and categorial grammar, which was actually developed by Mark Steedman while he was an NLP faculty member here at Penn. So why did this work in our case and not in the past? So I actually think that part of the reason is we happened across the perfect language for illustrating the potential for these syntactic models. So Urdu has many, many transformations that you need to make in order to get the word order to match English word order. And it's only got a small amount of bilingual training data, which means that we're unable to memorize in a way that we are for languages with much larger data sets, and we're forced to generalize. And this notion that it happened because we had a language with a divergent word order is actually quite interesting. So I generated this chart based on the natural distribution of word orders according to the World Atlas of Language Structures Online, where you can see that the two major categories of languages are subject-object-verb languages like Urdu and subject-verb-object languages like English. But if you just do a survey of the types of the languages that we study in statistical machine translation, you'll see that these verb-final languages are massively underrepresented, and the subject-verb-object languages like English are massively overrepresented. So in a way, it's sort of like, no duh, of course we're not seeing improvements. We're looking at the wrong languages. We don't need to make drastic transformations that would necessitate this syntactic formalism in order to translate between languages with similar word orders. Part of the reason for this focus on those languages is that we tend to work very opportunistically in statistical machine translation. So we tend to look at languages for which there's lots of readily available data. So for languages like French English, we have tons of data. So we've got this large billion-word parallel corpus that I assembled myself in my spare time as a hobby one year. We have large data sets produced by DARPA. Like we have about 250 million words worth of Arabic to English and Chinese to English. And then for any of the European languages, we can pretty easily harvest 50 to 100 million words by grabbing the proceedings of the European parliaments. But most of the time, we're in this condition with having a very small amount of data like Urdu, or even worse, having much, much less data than that. So I'm now going to turn to the notion of what should we do for languages for which we have no data. And one potential solution is simply to create the data at low cost. So the experiments that I've been working on are crowdsourcing experiments via Amazon Mechanical Turk. So Mechanical Turk is a crowdsourcing platform that's an online marketplace for work. And I think it was really designed with machine learning in mind. So you can see even the subtitle of Mechanical Turk is artificial intelligence. And the basic unit of work in Mechanical Turk is called a human intelligence task. So essentially it's set up to try to do tasks that are currently difficult for computers but are incredibly easy for people. So here's a random sample task from Amazon Mechanical Turk. This requester has posted a bunch of scans of postcard and asked Turkers to enter 5 pieces of structured information. So you can see that it would be hard for a computer vision algorithm to do this because the text is not linear, it's occluded by the stamp. But people can quite easily just read that and type in those 5 pieces of structured information. And in return for that, the requester pays them. And in fact, he pays them 1 penny, which apparently was the same amount that it cost to send a postcard in the 1800s. So this is one of the really seductive aspects of Mechanical Turk. We can create data very, very inexpensively, like surprisingly so. But I have to warn you that that is a bit of a gateway drug. So for a while, I was the 6th biggest requester on Mechanical Turk by volume. And so I've gone from spending $150 at a pop on Mechanical Turk to now, over the past 2 years, having spent more than $150,000 on it. So Mechanical Turk is really set up for these small, discrete tasks that anyone can do. So an open question was, can we use it to do much more complex tasks that require specialized skill, like translate? Oh, my Urdu is not showing up very nicely over there. That's all right. So in order to test this, I posted a bunch of Urdu sentences, which were professionally translated by translators hired through the Linguistics Data Consortium. And then I paid non-professional translators on Mechanical Turk to create the same set of sentences. And you can see a sample here. So what we'd like to do is just simply quantify how good the professionals are and how good the non-professionals are. So we can reappropriate the blue score that we normally use to measure the quality of the system outputs to measure the quality of professional translators. So we'll compare one translator against the other 3 that translated the same test set. And then we get an average and a standard deviation for what we would expect for the level of professional translation quality. And just for reference, for this set, there's our machine translation score. And then without any quality control, the Turkers are doing terribly. So they're doing not much better than our machine translation system, which admittedly is a pretty awesome machine translation system, but this is disappointing. So what we're going to do now is think about different ways of improving the quality of non-professionals so we can push them up into the range that we might expect from professionals. And the way that we're going to approach this is the fact that doing translation on Mechanical Turk is cheap enough that we don't have to just translate every sentence once. We can do it redundantly. And so each row here represents 4 alternative translations proposed by 4 separate Turkers. So the task is now going to be to design a machine learning classification system that can either predict who the best single translator is, or on a sentence-by-sentence basis, pick out the best translation of that particular source sentence. And you might think of even fancier ways of doing it, like creating a lattice from the 4 alternatives and finding some path through that lattice that's better than any of the single translations. So essentially what we're doing is just designing a set of features that we think will be useful in picking out the best translation, and then applying logistic regression to estimate the weights of each of these features. So we have a bunch of sentence-level features, so we can calculate a language model probability score for each of the translations that the Turkers have provided. We can look at how often the n-grams in the Turkers translation matched against the Google n-gram corpus. We can look at a variety of features about the Turkers themselves. So in addition to soliciting translation, we gave them a little survey of their language skills. So we can say, how long have they been speaking English? Is Urdu their native language? Where do they live? And use all of these things as features in our model. And in fact, we can do interesting things with Mechanical Turk, where we do a second pass through and have a separate set of native English-speaking Turkers vote on each individual one and what they think is the best English. And moreover, we use a small amount of calibration data that's been professionally translated so we can set these weights. So now we've been able to go from this situation to this situation where using the predictions of our model, we're able to push the quality of the non-professionals up into the range that we might expect from professional translators. And in fact, there's even additional room for improvement. So if we had an oracle that was able to always pick out the single best translation for every sentence, and this is an oracle, so it's unrealistically high, then we could potentially get better translation quality on average than the professionals. And if we had a slightly more realistic oracle that simply was able to tell us what the rank order of the Turkers are, then we could find ourselves in the situation of being at exactly the same level of professionals. So the really exciting thing about this, so that's really promising in and of itself, but it's paired with the fact that the translation expense is now an order of magnitude cheaper than the cost of professionals, including all the redundancy and including the cost of the small amount of calibration data that we had from the professionals. And if we found out more effective ways of doing the quality control, then we could get as cheap as 1/60th the cost of professionals. And moreover, we can get translations really quickly. So the figure here plots the rate of return on translations for a variety of languages. So over a course of less than a week, we're able to translate more than 500,000 words worth of Tamil data, which is the steep line there. And Mitch mentioned that I'm currently conducting the study on Mechanical Turk to try to translate 10,000 words in 100 languages. And this is going to be a better informed version of this pilot study that I did to try to see what kind of languages the Turkers actually speak and what demographics we have. So ultimately, our goal would be to choose some set of languages to translate and create training data for new statistical machine translation systems. So one set of languages of interest is dictated by DARPA, not necessarily by linguistic features, but it seems to actually have some pretty cool linguistic properties. And DARPA has a big focus on Arabic translation. And over the past 5 years, they've built really amazing machine translation systems for Arabic, but not for the different varieties of Arabic. So they, although we call Arabic one language, what we're really referring to is modern standard Arabic, which is the liturgic written form that's taught in schools. Individuals don't speak MSA at home. So everyone has a dialect of Arabic that they speak. And so, for instance, my PhD student, Omar from Jordan, speaks Levantine Arabic, and he cannot understand a Moroccan Arabic speaker. So many of these are mutually incomprehensible. So the upshot of that for machine translation is that although we can translate modern standard Arabic sentences quite well now, if you fed the system an equivalent Levantine sentence, the translation quality is terrible. And so you can see a lot of these words here are simply being transliterated by the system because they fell outside the vocabulary that was ever observed in the MSA training data. So the system is just wildly guessing at what they sound like rather than actually trying to translate them. And in many ways, that's the same effect that you might find if you tried to import Portuguese into a Spanish to English translation system. And this is not unrepresentative. It's actually generated by a pretty good machine translation system. So really what we would like is some way of collecting dialect data. But the written form of dialect is actually really hard to come by. So almost all publications are written in MSA. So if you go online and find a newspaper, it's always going to be written in MSA. So my student Omar had a great insight, and that's that with the rise of social media, we're actually getting a lot more written Arabic dialects. So he went and for all these online newspapers, harvested the comments and found that there's actually a really good representation of dialects in the comment section of the newspapers. So this newspaper happens to be published out in Egypt, so we observed a lot of Egyptian segments within the comments. And so what we did to start this project was we hired a bunch of Arabic-speaking language informants using Mechanical Turk, and they manually labeled 150,000 online comments gathered from newspapers published from a bunch of different Arabic-speaking countries. And then using this training data, we were able to train a simple classifier that achieved reasonably good accuracy. We went beyond that in that we hired these informants to also translate the segments that had been labeled with Arabic dialect. And in total, we translated 1.5 million words worth of Levantine and Egyptian combined. And this was part of a pilot study for the latest DARPA thing that BBN hired us to do. So we retrained BBN's system using the dialect corpus and compared it to a system that was trained only on the MSA data that had been made available by DARPA. So you can see that the effects that we observed before of trying to translate segments of dialect using the MSA system produces terrible, terrible translation quality. But then when you retrain the system only on the dialect segments, only on the 1.5 million words worth of dialect that we created, then you get much, much more sensible translations that come really close to the reference. So things that were previously incomprehensibly translated as God, you, the atmosphere are now translated as this is why the weather is so cold, or do you think about a joke long translates as calm down, we're only joking. So we can quantify this again using the BLUE score, and in fact we find almost another 6-point BLUE score improvement. So I thought that that was going to be a once in a career thing, but it turns out to be a once every couple of years thing, where we've moved from the MSA trained system to the dialect only trained system, and find that we get radical improvements when we're translating both Egyptian and Levantine dialects. And what I found to be fascinating was when we combined the two data sets, when we added the MSA on top of the Levantine and Egyptian, we actually got no improvements from that. And that went counter to my intuitions because I thought a lot of the problems were simply coming from out of vocabulary items, and you would think that that would further improve the quality of the MSA, but it turned out to be not the case. And the upshot was, in fact, for dialect translation, this 1.5 million word parallel corpus that we assembled using Mechanical Turk was better than the 200 million word corpus that had been created by DARPA. And moreover, we did it in a 2-month period for less than $50,000, where the other data had been assembled over a 5-year period at the cost of tens of millions of dollars. So the value of this, I think, is hard to put into context. I mean, this will allow us potentially to cheaply and quickly create training data sets for a range of new languages. And in fact, I think this actually expands out to a lot of different tasks. So I feel like I've learned to think about problems in a different way before and after I got exposed to this crowdsourcing stuff. So if you have a problem that you just wish you could solve if only you had data, let me know and maybe I can help you. So I'm now going to turn to the idea, and this is quite a speculative idea, of what if we didn't want to have to rely on these by text? What if we just simply eliminated the dependency entirely and tried to reimagine the models such that we could estimate their parameters using monolingual texts instead of by texts? So the idea of using bilingual parallel texts for translation has been around for a long time. So it's really kind of old school. So What I'm interested in is thinking about looking at the huge volumes of monolingual texts that we have access to via the internet. So here's a bunch of newspapers that are published in different languages, but I can tell that they're all talking about the same subjects, even though they aren't translations of each other. So the intuition behind this is maybe there's some weak signal across this large volume of monolingual text that we could take advantage of to actually learn translations. So one notion would be to look at the distributions of words over time. So these histograms, the red lines show the frequency of the English word terrorist on different dates, and the blue lines going in the other direction show the frequency of two different Spanish words, terrorista and riqueza. So you can see that the terrorist and terrorista almost look like they're reflected across the axis. So we're going to say that things that have a similar distribution of frequencies over time are potentially good translations of each other, and things that have very different distributions over time are probably not very good candidate translations. And riqueza means wealth, so it wouldn't be an especially good thing. So we can pull out the best translations according to this similarity of distributions of frequencies over time. And we can see that we get some really nice translations for the words like Eolica. We get wind, which is a valid translation. And then we get a lot of terms that are related but are not good candidate translations. And similarly for words like Istanbul, we correctly get Istanbul as the translation, but then we get a bunch of related terms like Erdogan, who's the prime minister of Turkey, or Ankara, the capital, and then membership negotiations, which is what Turkey is constantly engaged with the European Union. So this is like one weak indicator of translation equivalence. We can think of others. So we can borrow this idea of vector space models, like latent semantic analysis, and potentially use this to translate if we have some way of projecting from the vector space of one language onto the vector space of another. So the idea here is to just look at all of the contexts in which a Spanish word like crecer appears, and then build up a vector space representation of it, saying, here are the frequencies of the other Spanish words that it co-occurs with, and that's going to be its signature. And then we'll use a small seed bilingual dictionary that crucially does not include the word crecer, and we'll use that to project on into the vector space for English, and now we'll have a sparse vector that's projecting crecer onto English vector space, and then compare that for two vectors representing all English words, and then find the most similar one according to cosine similarity or whatever your favorite similarity metric is. And we can see again that we get a variety of high-quality translations emerging as the best suggested translations along with this method, and then a number of alternatives that aren't good translations, but you can see would be contextually related. So with wind, we also get things like geothermal, probably because they both occur in contexts like clean wind energy, clean geothermal energy. And for Istanbul, we're now getting a completely different set of similarities, different than the frequency over time, and now we're getting other place names. So we can imagine a bunch of these kinds of weak indicators of translation equivalence. So we can think about similar spellings, which might help us identify etymologically related words, or we could think about topics. So we pair Wikipedia articles via their interlanguage links, and although they're not translations of each other, the frequency of words across those topics are usually a good indicator that the individual words might be. And we assemble a slew of these kind of weak indicators of translation equivalence. So the other thing that we need to pay attention to in machine translation is the idea of reordering. So the way that we estimate reordering in bilingually estimated machine translation is to take a word-aligned sentence pair, like we saw before, and estimate a distribution over 3 possible configurations. So we say, how frequently is this phrase pair come in a monotone order compared to the previously translated phrase? How long does it come swapped with the previously translated phrase? And how often does it come at some discontinuity compared to the previously translated phrase? So we then estimate the probability of each of these three things given a particular phrase pair and use that to inform how we reorder. And so what we're going to do now is, instead of using those bilingual sentence pairs, we're going to draw independent monolingual sentence pairs that each contain two words in our phrase table and pairs of their translations. And then we're going to look at what order those things come in across many, many sentence pairs. And we can see that even though these are not good translations of each other, we can potentially get some signal there into what the distribution should be for those pairs of phrases. So before, when we were estimating these things bilingually, we could learn that these two phrases are swapped from that directly observed bilingual sentence pair, but now we can learn that similar sorts of swapped orientation from these independent monolingual sentences. So the German sentence here translates as creating a Facebook profile is easy. Okay, so what we'd like to do is now see how well these different monolingual estimates do at replacing the bilingual estimates that we usually use for statistical machine translation. So we've now performed a really clean room experiment to see how much of the translation quality we could restore if we lesioned out each of the different parameters estimated through bilingual. And I have to stress that this is really idealized. So we're assuming that the phrase table is the same between these two experiments. So God has handed us a phrase table, which we know contains some good translations in it, but also contains a lot of noise. And so what we're going to do is then take that phrase table estimated from this particular bytext and delete all the translation probabilities that we estimated bilingually and restore them monolingually. So here's the estimates. So this is the translation performance of the standard phrase-based model that's been bilingually estimated. If we then cut out the reordering thing, we don't suffer too much. If we keep the reordering model and cut out the translation probabilities, then we drop pretty considerably. And if we cut out both the reordering model and the bilingually estimated translation probabilities, then we do terribly. So this is now just being governed by the monolingually estimated language model. Now each of the color bars on the other side corresponds to what we're restoring. So now the orange bars represent only having the reordering model. And the green bar is only having the monolingual equivalence of the translation probabilities. And finally, we have both the translation probabilities and the reordering model, and we're able to restore about 80% of the translation loss that we got by cutting out all the bilingual estimates. And in fact, we seem to be discovering something that's interesting and maybe orthogonal to what we're getting from the purely bilingual estimates, because if we add the monolingual estimates alongside the bilingual estimates, we get a small improvement over that. Okay, so what now? So now we're interested in getting rid of that idealization, and this is the part that we're currently working on. So really what we could do is simply compare the vectors for all English words and phrases against the vectors for all the foreign words and phrases. So unfortunately, that's intractable. So if we just took observed phrases from a small corpus, then we'd have on the order of 10 million English unigrams, bigrams, and trigrams, and we'd be comparing those against roughly 10 million Spanish phrases up to length 3. And then the dimensionality of our vector is really going to compare on a number of factors, including the size of the bilingual dictionary available, but we might choose the 10,000 words that I'm creating on Mechanical Turk, and that would leave us with something like 10 to the 17th comparisons, which is probably not going to happen. So we're currently investigating a number of mechanisms. So I've been introduced to locality-sensitive hashing and approximate k-nearest neighbors by a colleague of mine at Hopkins named Ben Vandermee. And so I'm finding these to be really, really exciting topics. And if you work on it, and I gather that Lyle and Dean and their students are working on these topics, I really want to work with you. Like, I think that these are really, really exciting things, and this is a really exciting application of dimensionality reduction and approximate k-nearest neighbors. Okay, so now I'm going to pivot onto the final topic, which is now instead of doing the task of translation, we're instead going to see if we can reuse the data that we have for statistical machine translation to do an interesting, different task, which is one aspect of natural language understanding called paraphrasing. So what are paraphrases? They're simply different textual representations of the same meaning. So we have synonyms like cup and mug. We have phrasal paraphrases like the king's speech or his majesty's address. We have awesome templates like the ones that Nitin worked on in his thesis, and various patterns like X devoured Y is the same as Y was eaten by X. So what are they good for? So they're actually good for a huge range of natural language processing applications. So anything from automatic summarization to question answering to information retrieval to essay grading, which ETS is interested in. We have some friends over at Drexel who are looking at adversarial stylometry, so trying to evade automatic authorship detection by rewriting your text in a way that doesn't represent the way that you normally write it. So a huge range of potential applications if you had a large set of paraphrases. So the way that we generate paraphrases is we look for some phrase that we want to paraphrase, like thrown into jail, and we look it up in our bytext and figure out what foreign language phrase it aligns to. We then look for other instances of that foreign language phrase and see what it aligns back to. And so as a result of being able to pivot through this bilingual shared phrase, we're able to equate thrown into jail with imprisoned as a potential paraphrase. And the really neat thing is because we have lots of variation in our bilingual parallel texts, and because we can use bilingual parallel text not only for English German, but also for English Arabic or English Chinese or any of the English to X languages, we get a huge range of alternatives extracted in this fashion. So for paraphrases of thrown into jail, we not only get imprisoned, but we also get jailed, arrested, incarcerated, locked up, taken into custody, thrown into prison. So interestingly, we also get a number of ones that are pretty bad. This partially arises due to the fact that we're using automatic word alignments, which are inherently noisy. So what we'd like to do is be able to take this candidate set and rank them. So I've defined a paraphrase probability that incorporates the different translation model probabilities that are inherent to this type of data. And we can also combine it into a log linear model and add a lot of other interesting features like the distributional signatures that we're using under the translation without parallel corpora. So I've recently been pushing this beyond just phrasal paraphrases. So I've been looking at using this technique to learn meaning-preserving structural transformations in English. So here are two synchronous context-free grammar rules for English to French. And these are back to the syntactically informed models that we're now using. And we can actually combine those into a very interesting pattern. So we can look at this general rule for English, which is rewriting the possessive apostrophe S in this fashion. So we get something like the quadricopter's subcomponents rewriting as the subcomponents of the quadricopter. And we can go looking in the large-scale paraphrase grammar that we extract in this fashion and find a huge range of English transformations in this data. So we not only find the possessive rule, but we find things like the dative shift. So give the book to Mitch, give Mitch the book. We find the fact that we can freely move adverbial phrases in English. We even find interesting things like late verbs. So to make a decision, to decide. So the upshot of this is we now have a synchronous grammar that essentially allows us to translate from English to English, right? So we can actually use this for a huge range of sentential paraphrasing tasks, which we can also think of as text-to-text generation task. And we can reuse the machinery that we have in place for statistical machine translation now in a non-naive fashion. So we have a huge paraphrase grammar for English, and we can customize that to a particular task that we're interested in by trying to hone it in a set of very specific ways. So we need a set of development data that illustrate the phenomena that we want to model. So for instance, if we're interested in the task of rewriting sentences to be shorter, a sentence compression will have long English sentences paired with their equivalents that are shorter. And here we only need about 1,000 sentences. So we don't actually need the million sentence pairs that we had for statistical machine translation, because this development data is just used to discriminatively train our weights. We need an objective function that actually takes into account the particular type of task that we're interested in doing, and a set of features that'll allow us to actually customize the performance so it'll meet that objective function. And finally, we could add in grammar augmentations that we didn't learn automatically. So if we wanted to create a rule like the adjective superfluous can be written using epsilon, then we could add that using some domain knowledge. So here's an example of using the paraphrase grammar that we extract from an English-French bitext to do sentence compression. So we get the sentence, 12 of the cartoons that are offensive to the Prophet Muhammad, or the phrase rewriting as 12 cartoons insulting the Prophet Muhammad. And that actually encodes a lot of really interesting transformations, not only lexical paraphrases, but also a reduced relative clause, the fact that predicative adjectives allow you to delete the copula. It's really super cool. So I think we can actually not only apply this to the single tasks that we've done so far, but to a wide range of tasks. So we're going to look at rewriting sentences to be simpler for young students. We're going to look at trying to correct English as a second language errors. We even have some plans to do fanciful tasks like poetry generation and rewriting legalese into plain English. So I'm going to sum up here. So I've kind of given you a whirlwind tour of all the different topics that we're working on in my lab at the moment. So we've seen that we can get state-of-the-art results in machine translation by improving the underlying models. We've looked at expanding the capacity to do translation to extend to new languages by collecting training data at extremely low cost via crowdsourcing. And I think that actually has general application to a huge range of machine learning applications. We've reimagined how the models can be estimated by replacing the bilingual texts that we're training them from with distributional properties of huge volumes of monolingual texts. And finally, we've shown how the data that we can use for machine translation and all of the models and machinery can be reappropriated for really, really interesting tasks that touch on natural language understanding as well as translation. Okay, thank you very much. Yeah, so I think the key to that, so we use discriminative training to set the weights of our log linear model that we use for statistical machine translation by trying to maximize some objective function. So in machine translation, we're maximizing the objective function of blue, which is that scale that I've been showing in all the graphs. And that just measures overlap with reference translations created by humans. So as we're increasing the overlap against human translations, we're assuming that the translation quality is getting better. But it turns out that that's a very inappropriate thing to do to optimize to for paraphrasing, because you may end up getting some trivial set of paraphrases where you're simply rewriting the sentence as itself, right? Which is a valid paraphrase because it's meaning preserving, but it doesn't introduce any variety. So I think the key for applying the techniques that we're using in statistical machine translation to other text-to-text generation tasks, monolingual text-to-text generation tasks, is to come up with an objective function that measures what we want. So it should probably have some component of measuring overlap of a human reference, but it should explicitly encode something else. So if we want something like sentence simplification, we could look at readability scores, like the Flush-Kincaid score. We could look at that, which takes into account the average number of syllables per word. We could explicitly encode the frequencies of the words that are being output and try to bias the system towards choosing more frequent words. rather than less frequent obscure words. So it's really just a matter of defining that objective function in a way that's meaningful for the particular type of monolingual text-to-text generation task that you want to do. And I actually think that that's really cool because it adds one avenue of research beyond just saying, this task is like machine translation, ergo I'm going to apply the machine translation machinery. That's always been a little bit of a pet peeve of mine that people do that, and I like now that we've formulated a way of doing it in this really nicely informed, non-naive fashion. Yeah, so I think that those are probably the two most important aspects of crowdsourcing is what's the incentivization, and then how do you do quality control to avoid noise that's either introduced by people trying to scam you to get that small financial reward, or through simply lay people not being able to do the task quite properly. So the incentivization is like a huge open-ended question, right? So it can range anything from kind of Louis von Ahn games with a purpose, where the incentive is just to do something fun, and you end up labeling a bunch of images, or it can be a sense of dedication or philanthropy. So we've done a bunch of tasks with Haitian Creole in the aftermath of the earthquake, or with Urdu in the aftermath of the Pakistani flooding, and a lot of the motivation of people contributing to those things is not financial, it's something magnanimous. So the thing that I really like about Mechanical Turk is it allows you to shortcut understanding what the motivation is for people participating by offering this financial incentive. It'd be really awesome to work with someone from Wharton to try to figure out what's the optimal pricing strategy on here, because now I'm starting to pay enough out that it would actually be good to have a very good underlying model. But so far, I've just treated it as an indication, like, here's a financial incentive. Do I find people who can do it at that? If not, bump it up slightly. So I don't have a science behind how I'm pricing things now. In terms of the quality control, I mean, that's really the crux of how you get this right. So the general mechanisms that I'm currently using is always embed a gold standard. So for any task that I want to do, I'm going to solicit not just one piece of information, but I'm going to solicit a collection of labels. And for some subset of that, I'm going to have a known answer that I should match against. So it's really easy in some cases. So for tiny little pieces of structured information like that postcard, it's simple to check, did they get the right answer or not? It gets much more complicated when you're dealing with complex things like translation, where there's not a single good answer. So for things like the 10,000 words in 100 language task that I've got up at the moment, I'm asking people to translate 10 words, and 2 of those words are actually the titles of languages that have an interlanguage link with English Wikipedia. So I can then check to see whether they got that right, and if it's an exact string match, great, I pay them instantly. If it's not an exact string match, then I take their translation and the gold standard English title and I post it to a second pass hit where I ask English speakers, are these things synonyms, or are they related, or are they not? And there I'm basically having English speakers grade the translation accuracy of the first pass translators. So that again comes at some sacrifice. So for any new piece of information, there's some overhead that I'm gathering by requiring that there be a gold standard embedded alongside it. So there's again really an optimization strategy there for cost that would be really fun to explore. But so far the cost has been low enough that I've kind of just been saying, I want this to ensure the quality is good, so I'm not going to pay attention to the cost. Correct. Yeah, That's absolutely correct. That's a really great, insightful observation. So in fact, I set it up that way purposefully because it was far easier for me to say, are the translations they're giving me back sensible? Because I can't read Urdu, so I can't make that judgment. So my initial plan was to cultivate a set of workers who I trusted, who could translate from from Urdu into English, which is their second language. And that's totally the wrong direction, right? So translators would object to translating in that direction. You should always translate into your native language. So my original thought was I'd then I'd grant a special qualification to allow only those trusted translators to translate in the other direction and just kind of let them go. So I did that, and it turned out for Indian languages, it was surprisingly hard for people to translate in the other direction for sort of crazy reasons. Like text entry in native scripts is really, really hard. People have Latin keyboards. So they were having to use things like Google Transliterate to type in their native script. And that ended up being that their effective hourly wage dropped really considerably, which makes my bleeding heart, my liberal bleeding heart really cry. But so another alternative that I've been thinking about is actually to have people continue to translate into English, and then to do a second pass hit where I annotate ESL errors. So I specifically identify the common types of errors that English as a second language speakers make and mark them up. So as a result, I'll have both improved translations, which are suitable for training my system, but also like a richly annotated data source of ESL errors that we could then use for further natural language processing studies. So this is actually sort of something that's on the rise, and that people like Joel and Nitin at ETS have awesome access to really cool data, but that most of us who aren't at these companies don't have access to. So there's been like a huge absence of this particular type of data that I think would be an amazing byproduct of trying to generate these translations, and would actually allow us to create a whole new, potentially popular subfield within natural language processing. Yeah, so that's an excellent point. So in our paper about this, which is being published at the European ACL this summer, which you can also grab from my webpage, we actually did an analysis to look at the frequency of words versus the accuracy that we would get it right using these weak monolingual signals. And you find that, as you would expect, less frequent words are much more difficult to translate accurately in this way. It might actually be that for some class of those rare words, we're in a good situation in that many of them might be technical terminology that shares the same root as the word in the foreign language, so borrowed terms. So we might be able to translate those well, but that's kind of an open question at the moment. So how do we get that set of very important words translating accurately? So yeah, great point. Bonnie? Yeah, so for all these results, the change in translation quality is so dramatic that we can basically measure it with any coarse-grained thing. But this is something that I have thought quite deeply about. So each year, Philip and I run this workshop on statistical machine translation, which has a set of shared tasks. So one of the shared tasks is we create a test set where everyone runs their latest and greatest machine translation system and produces the best output they can. And then we conduct a large-scale manual evaluation to have people rate that output, and we come up with a ranking of systems and individual translations. And then we use those human judgments of the system translations to validate the automatic metrics. So we've come up with a kind of secondary shared task for metric developers to say, can you get stronger correlation with human judgments than the BLUE score? And Actually, last year, ETS, like, you guys are awesome. So they applied their essay grader technology, the E-rater, to the problem of machine translation and actually found stronger correlation than a lot of other things. So the sorts of features that they have in their E-rater were, surprisingly to me, quite useful in ranking machine translation output as well as grading student essays. So a lot of people have been developing really interesting linguistically informed methods of judging translation quality that are way better than the coarse credule of blue. And so I haven't been working on that topic myself, but I've been facilitating a lot of work in that area by others.